Hi and welcome back. Today I am here with again another module of simulation in R, and in the previous three modules of simulation in R we had discussed about some of the examples which are based on simulation, but in this module we will take up something more. Here we will start with the discussion of the sample function, then we will discuss about how random samples can be simulated from a model made with linear model or a generalized linear model, and in the last part of our discussion we will be discussing about a library called RCPP armadillo. This is a very new one and a very popular one as well, and we will give some basic ideas of this library. So let us see what is there in this module. So in this module we are going to learn about the use of the sample function. We are going to know how to generate random samples from a model, and we will have some ideas of RCPP armadillo. So before going into some other objectives of the simulation function, let us talk about another important function which was absent in our previous discussion. So let us start discussing about the features of that one. So let us start with the thing that is done here and the function that it does actually. Primarily it helps us to pick or draw samples randomly when a vector of numbers are provided to us. Not only numbers, it can draw from a kind that might include letters as well. We will discuss about all these kinds of things in details here. So let us start with the syntax of the function. Here, as it had been given, sample function primarily has a syntax that is given here. It takes x, size, replace is equal to false, probability is equal to null as an argument. So let us take up these kinds of arguments one by one. By the x argument, one can specify the vector of elements from which one can draw the numbers. The next argument, size, is something which specifies the number of times, the number of items which are required to take out. The next argument, replace is equal to true, gives us the option of whether we are going to draw sample with or without replacement. By default, it takes equal to false argument. So the sampling is going to be a without replacement one. One last argument that should be mentioned is the probability argument. Primarily, as R says, it provides a vector of probability weights for obtaining the elements of the vector being sampled. So as we can understand, this will help us to execute an unequal probability sampling made with or without replacement. So this is what the argument says. Now let us think of some examples where the function is used to build up for our better understanding. So here, as a special case, suppose we want to draw a random sample of size 10 from the numbers 1 to 50. So what do we do here? We are using the numbers 1 to 50 as our argument, and which we would want to sample from. Next we are putting 10 here, since we have drawn a random sample of size 10 in this case. So let us see what we are getting here. We have here 10 random numbers from 1 to 50 without any repetition, since by default the function takes the argument replace equals false. Here we have set the seed to be 1, so we will be able to generate exactly this set of numbers further if we use the seed value. Again, if we use this function repeatedly, then the effect of this function gets nullified and of the seed function gets nullified, and we are having a fresh set here only. Again, repetition is not here as well, as it can be evidenced from the output. So no repetitive numbers are here. Now, let us do some experimentation with this. If we just write down the argument 1 to 50 within the sample function, then what happens? As we can guess, since no sample size has been specified here, so by default the function will sample 50 many observations, that is the whole sets of numbers. But since they are sampled out, so no longer they are showing the same order in which they have been given, but exactly 50 observations are there without any repetition, as it can be evidenced from the argument as well. Now, here look at the code. Just one argument is added here compared to the previous one. In the previous case, we let replace to take its default value, which is false, but here we are trying something different and we are using default equals true. So, these are the arguments that we are getting. Now, have a closer look at this. Since our with replacement sampling has been done here, so as we can expect, here we are actually finding numbers more than once. 17 is one such which is found at the very beginning and many a times thereafter. But since the sample size is not specified, so we are having total 50 many observations, but actually we are not getting each and every observations that are given within the argument. So, this is all about how we can handle numeric digits within the sample function. Now, let us see what if the arguments are based on letters. So, if we specify the arguments that have been given here within the sample function and then specify the size to be 10, then what happens is that it takes 10 random alphabets from the sets of 26 without replacement. Since replacement is equal to false is the default here. So, we are having a permutation of any 10 distinct numbers here. So, these are primarily the features that the sample function offers us. Now, let us take something new. So, before this we have done lots of experimentation with simulating random numbers. Then testing our statistical intuition, these are done in some of the previous modules, and we have done many more things with the generation of random numbers. But there is something which still lacks the discussion, and here we are taking up the topic and trying to explain it explicitly. Here, suppose our objective is to generate random numbers from any model. Let us start with something which is very simple, and later on we can keep on increasing the complexity of the model. The reason why this topic is included is that if you understand the principal idea of this, then it would be easier for you to draw samples from the model that you have proposed or will propose in future, and will be able to bring out some interesting features out of it. So, let us concentrate on this. Suppose we are dealing with the simple linear model, which is y is equal to beta naught plus beta 1 x plus e or epsilon, where this error part follows normal 0 3 square. Now, we are assuming x to follow normal 0 2 square. Along with this, some more things are needed to be assumed. So, just take up them one by one. Here we are having beta naught and beta 1, and we are fixing the values of beta naught at 0.4 and beta 1 at 1. So, let us see how to generate random numbers from this model. Now, for drawing random numbers, at first we are setting the seed value to be 12. This is very important because this would help you to return exactly the same random numbers which you are using here, and that would solve a lot more problems. Actually, as we know, the numbers that R provides are not actually random. It is a set of pseudo random numbers that R is giving R for us for our convenience. Now, we have set the seed arbitrarily, it can be 10, 30, 11 or any numbers like this. Here, as we have already fixed the specification of x and the error variables, which are normal with 0 mean and standard deviation as 2, and again normal with 0 mean and 3 as standard deviation. So, following this, we are specifying the x and e variables like the one given here. Now, we know there exists a linear relationship between x and y since it is a linear model that had been specified at first. So, just looking at the model, we can observe that here the mean and standard deviation of y as well can be calculated with a minimum amount of effort. So, by fixing the constant values, that is beta naught and beta 1 values in the model, we are having our y values here. So, this is what the y is. Now, let us plot the newly found y and x which were there before, which we had given, and let us see what happens. The plot that we are getting here will look like this. So, as it is evident from the plot, here x and y do have a linear relationship. We can also do a lots and lots of experimentation as well with this y. We can find what the central tendencies of it actually, and we can find many more out of it, and from it we can reveal some underlying things as well. So, do try this by yourself. Now, let us consider another example here. These two of the examples say almost similar thing instead of just a small change. Let us see what is that. Here we are considering the same linear model, but instead of taking x to be a normal random variable, what if it is actually a binary one? So, the problem is all about taking a binary random variable. So, just change a few things and you will reach towards our objective. Look at the code that had been given here. Here, instead of putting the random samples that has been drawn from the normal distribution, since we are considering x to be a binary one, hence we are drawing 500 random samples from a binomial distribution when size equals 1 and the probability of success equals 0.5. In case of the error component epsilon, again we are drawing 500 random sample from a normal distribution which has mean 0 and standard deviation 3. So, this is what we are inputting here. So, by this way we can have the y values corresponding to a simple linear model which contains x as a dichotomous variable. If you wish, you can see the values of y as well, and also as we have talked earlier, as a next step you can always take the summary statistic of y from this, but we are not doing this here. So, as a next step we are doing the thing what we are supposed to do. Here we are plotting the values of x and y through a scatter diagram, and let us see what is happening here. Look at the graph that have been given here. Here, since x takes either 0 or 1, so that have been reflected here, but as we can understand that the y's are continuous, but also here also we are having a linear trend which is pretty much obvious from the plot. So, this is how the plot of x and y looks like, where we are having a linear model with binary x and continuous y. Now, our next objective is to deal with a slightly complicated model. Unlike the linear model that had been discussed previously, here we are having a generalized linear model. Suppose here we are taking y to be a Poisson random variable with mean mu. So, what do you think? What kind of the variable y should be here? In the two previous cases, we had assumed y to be a continuous one, but here since y is taken to be a Poisson one, so here it is a count variable. Now, as we can understand, things are not as simple as it used to be in the case of a simple linear model. The basic difference between the two is that the error distribution is no longer normal here, since it is a generalized linear model. Actually, here it is a Poisson one. So, here as we can see the outcome variable y is taken to be Poisson 1 and the log of mu here will follow a linear model with beta naught as an intercept and beta 1 as a slope, and these beta naught and beta 1 are some unknown constants. Also the predictor variable is x here. So the first thing that had been done in the previous case as well, we are fixing the values of the unknown constant, and exactly that has been done here. So this is what our model is, and if we simulate from this model, then we are going to have a Poisson data. So let us see how we can get this in R. So here, as we can see, we are setting the seeds to be 10, and as we know, this requires for our convenience. Next, as it had been told earlier, we are specifying a normal predictor here, and we can see here that the x variable contains 500 random numbers from the standard normal distribution, that is here it has been taken as mean 0 and variability is specified to be 1. Now our next job is to have a linear combination of these predictors, which is beta naught plus beta 1 times the predictor variable x. This is actually the log of mu. So log of mu is equal to this thing, 0.5 plus 0.3 into x, since we have fixed the value. And as we can see, we are storing the values of these within the variable log underscore of underscore mu. So this is what the log underscore of underscore mu variable is. We can call it log of mu. Now as we know that the mean of the Poisson distribution is e to the power this 0.5 plus 0.3 into x, that is e to the power log of mu. So we are generating 500 random samples from the Poisson distribution using the rpoise function, and the mean, that is lambda, is specified to be e to the power log of mu. Exactly this thing has been given here. We are storing these values in the variable y, and hence this is what our y variable actually is. We can see the values of them. If we want, we can just call y and they will give you, R will give you the y values. Also, as always, we can get the summary values and things related to this, and we can always explore some interesting facts that might be known or unknown to us. Now our next job is to plot, as we know, the x and y. So using the plot function, we are plotting the things that we have given as output, that is x variable, and the variable that we are getting as, so the x variable is an input and the y variable is an output. So this is what the plot is. We are plotting here x versus y. So using the plot command, look at what we are getting here. The plot clearly shows a Poisson data with the y is taken to be a count variable and x to be a continuous variable. And this also shows a clear linear relationship between x and y. So here, as x increases, the count for y becomes larger and larger. So this is what we are getting from the x and y plot, scatter plot. So starting from the first module of simulation in R, our discussion was primarily based on some well defined aims and objectives, which includes to test our statistical intuition, to test the power of, to compare the power of two or more tests, and many more. In this module, we just come to know how we can simulate data from a standard linear model. Even if it is the case that the model is a bit complicated, then also we know that how to handle them and how to draw random samples from it. So things are quite clear regarding this as of now. We have come across a lot of examples and tried to materialize or visualize what we are thinking or what our intuition dictates us to think. So we have come across all these things, but let's have an overview of something which is indeed a bit more complex, but this thing gives you how efficiently you can run a code. Here we will give you just an overview of this. We are not going to give you much details. We will try to let you know the instances where things like this are used more efficiently. For this, let's start the discussion with an idea of RCPP armadillo. So it's a heavy name, and seeing this you might be thinking that the whole thing is going to be that heavy. So, let us see, let us find how complex is it actually. At first, let us find the RCPP, what RCPP actually is. Primarily, RCPP is an R add-on package. Now, the question is what actually it does. I mean, why do we require this? Basically, RCPP helps you to extend R with C++ functions. So, how it works? Firstly, it can be used for anything. It can be some small add-on functions which is meant for accelerating the computation. And how does it do all the works? It does this by replacing an R function with its C++ equivalent. So, basically this is what the function is doing. Also, it can be used as a building block in entirely new research computing environment. As we can understand, RCPP is relatively new, but the catch is that it has already become widely popular among us, that is the users and those who develops many things in the R community. Now, let me give you some statistics regarding this. RCPP is now the most popular language extension for our system and used by over 100 CRAN packages as well as 10 bioconductor packages. Those are very much useful, as you all know. So, the next thing is what armadillo is. Primarily, armadillo is a C++ linear algebra library. So, what is the objective of this? Basically, it helps us to maintain a balance between the speed and the convenience of using. So, let us find what are the objectives that it supports. The things that it supports includes integer, floating point and complex number. Not only this supports subset of trigonometric and statistics functions, various matrix computations, matrix decompositions are also included here. Another important thing that is really welcoming about this RCPP includes recursive templates and template meta programming. One thing that I want to mention is that this library will be the one which we would love to use when we choose C++ as the language of our interest or the language that we use for our convenience. And as we know, from the day we have started using programming, that C++ is always preferred due to primarily two of the things. One is the fact that it provides an excellent speed, and another is that it has really significantly high integration capabilities. So, from these features you must have guessed that it would really provide us some really well organized simulation facilities which is faster than even one can think of, and one can definitely use this function, this library one can definitely use this library for his own purpose. So, as we have seen from this module, we have come across the syntax of what the sample function is, and we came to know how we can generate random sample from a linear model or a generalized linear model. We come across such situations where y comes from a normal variable, and also where y is a binary random variable. In the last part of the discussion, we had discussed about a very new topic, which is a very new library called RCPP armadillo. Indeed, many things can be discussed regarding this, but we haven't discussed a lot more things regarding this. Keep on experimenting with this package after knowing this. It's really very helpful for your future knowledge.